All right. Just like that, it's 3:30 on my clock, so we're back. It'll take a second for people to fill in. Uh, Thanks, everyone. Thanks to all the students and postdocs. I saw a number of great posters, had some great discussions. I hope everyone else did as well. Now that we're back here, I'm going to turn this over actually very quickly for our next session, which is on Labs of the Future. And that's going to be moderated by Kyle Saleeby from Georgia Tech and Katelyn Jones from the group at NIST. So Kyle and Katelyn, I'll let you take it away and run our session.
Okay, sweet. So, hi, welcome back, everyone. So we'll kind of do this where we'll kind of alternate introducing people, and we'll kind of give a little bit of an introduction to everybody, and then every speaker will have about 5 minutes to kind of talk about their current work. And then we will go from there. So first up is going to actually be David Elbert. He's a faculty research scientist at Johns Hopkins University who operates at the nexus of data science, AI, cyber infrastructure, and material science. He leads development of event-driven platforms for autonomous data processing, leads the Army Research Lab Center for Data at the Speed of Extreme Materials Discovery, and serves as the Chief Data Officer for the NSF Paradigm Materials Innovation Platform. As a leading voice in modern materials data infrastructure, Elbert plays a central role in the Materials Research Data Alliance, which we are all here for, where he champions the fair data principles to ensure materials research is findable and machine operable. His current work is a driving force in autonomous materials science, focusing on the development of self-driving, AI-driven self-driving laboratories that integrate robotics and real-time data loops to radically accelerate the discovery and characterization of materials for extreme environments. And with that, I'll let you kind of take it away, Dave.
Thank you so much. I'm going to share some slides. Are people seeing slides or presenter notes or
Yes, we can see them.
We can see them.
perfect? Thank you. Then I'm going to hide my floating meeting controls and try to keep this brief. I was thinking about this panel. Todd Huffnagel is our lead PI in the lab I'll talk mostly about today, but he's on sabbatical, so I get the joy of coming in and doing that. I hope that's not overexposure in a MaRDA meeting. But I realized I'd already given some talks with future in the title, and I think what really may surprise a lot of people is how fast the future is getting here, how fast things are happening in PCLs or labs of the future. So I really want to highlight that by pointing out 2026 is not 2023. Lots of stuff have changed, and really this focus on moving towards automation and eventually more fully threaded autonomy is a great carrot for making things happen. A lot of the work here comes from funding from a couple of different sources, and I really want to thank a NASA STR award, the ARL HTM DEC group has been really important, as well as ARL awards for this lab for AMD and foundational things from the NSF. And this is my great team who really makes all this happen. So I was thinking about this and thinking that, in MaRDA, we don't want to forget certainly fair data. And what we were doing just a few years ago was really focusing on how we would frame things in FAIR and produce publication of FAIR data sets associated with things. So most of this work actually comes from Paradigm, and that we publish a lot of data sets. In fact, we have the second largest corpus of DOI-bearing materials data sets, second only to the Materials Data Facility, but for experimental data sets, I think we may be the largest that self-host those at this point in time in the materials world, which is kind of exciting. But we worked on interoperability of formats and being able to reproduce analyses, producing knowledge graphs. This particular knowledge graph comes from Ray Ariabe's great HTM-DEC birdshot project that we work on the data for. And then there are MaRDA things like automated metadata extractors. So FAIR has really meant curating data sets and minting DOIs, linking back to things to be able to show the underpinning data for work, and advancing ideas about FAIR. But in the labs of the future, FAIR is no longer just something we do to support the science, right? It's absolutely foundational, in my view, in how we actually link things together, and it has to start at the very beginning, and things have to be born fair, and I'll show you some of how we do that. to motivate the basic things that make labs of the future particularly valuable and interesting. I think everybody already knows most of these, but we really get to execute complex things faster, more reliably, with a deeper, more interesting opportunity to look through the parameter space of interest. And that means that we can then facilitate AI that can jump over current limitations. We have more traceable, testable, reproducible approaches and really much more capable things. I think I paraphrase Jim Warren from yesterday that labs of the future are sort of data producing engines. But really, to make that data more meaningful and to feed the loop, there are some central concepts. So I thought my role in sort of presenting what we do is to say a few things and then let that lead to discussion and be provocative. So we could make lots of lists of central concepts. I think I highlighted in orange that obviously everything has to be automated. Really everything. We need to get the humans out of the loop, and few of us have been able to do that completely, but we're working towards it depending on the space. And then we think a lot about instrument augmentation, automation, but I really want to think about how we automate data and metadata and how we think in terms of workflows. The little Venn diagram on the right shows that we have lots of kinds of workflows. And in my experience, people think about workflows very differently if they're computer scientists or they're data scientists or they're working in a lab or they're writing AI agents and agentic approaches to things. So we need to make those workflows all composable and computable and actually be automatable as well. So there are some empowering concepts that we lean into a lot. And I think of everything as a workflow and everything as some sort of a service. Everything can be offered as a service because then we can really take the humans away from that. In a simplified way, in a lot of talks, I'll often mention that automation plus decisions is how we get to autonomy. But this automation and even the autonomy is a web of events. And so we need some sort of semantic connection between things. And I'll focus in there a little bit today because that's really a MaRDA type of concept. So this is the Artificial Intelligence for Materials Design Laboratory at Hopkins, AIMDL, we call it. It's sort of a lab of the future facing PCL, if you will. On the left, you see some views into the lab. It's a beautiful space. On the right is a bit of a artist cartoon of it. This thing that looks like a staple here is a conveyance that moves samples around, and then we have a bunch of robot arms that pick samples up and move them in and out of machines that run from fairly standard high-value machines that can be purchased and present in a lot of labs, like a profilometer or nanoindenter. We have a development station. But then we have an X-ray instrument that there are only a few of in the country. It's sort of a synchrotron in a box. I'll talk a bit about that. And then an impact station, the laser shock impact station. An important concept for us then to lean into those things are that we use a client-server architecture, but we integrate between client-server architecture for automation and control of the instruments using sort of the Industry 4.0 standard, OPC UA, which lets us actually control instruments, control robots, do that in a secure way. And then we use an event-driven layer of live streaming with packages we've developed through NSF DIMREF type of projects so that all the data that comes off the instruments is also streamed, can run through orchestrated workflows. We have ways then, of course, through an API and web clients to control the instruments and through the data portal to auto-process things. So the ability to, in an automated way, handle that data and all the scientific data to be linked is really important to us. And by making it event-driven, we attack one of the principal problems with scaling things. We see a lot of development early on in these types of labs of small isolated units and then bringing in extra pieces, but point-to-point integration. If we're going to have all of our data automation, all of our workflows, all of our instrument automation have to one-to-one communicate between things, it doesn't scale, right? That scales quadratically. So really, in a sense, autonomy is bottlenecked by interoperability and how we conceptualize the way we put the lab together. So I'm going to run a little video showing you something running in the lab. So you're looking inside this X-ray instrument Maxima in the one camera on the upper left, and you have two views of the outside. The conveyance is below. The robot's going to pick a sample up. my favorite part of the video. It's going to pass the sample through the door, leave it inside the instrument. Of course, it's a high energy X-ray machine, so it's highly shielded. So there's interaction here through our one set of automations that takes care of closing the safety interlocks in the door, and then a robot inside will pick the sample up. And this is where I think it starts to get really interesting for MaRDA, which is if you watch the robot here, it'll be moving along in front of the X-ray source. There's a large 2D detector. This is an Eiger detector here. And on the right, we've actually had to slow it down so you can see it in the movie, but this is the data portal. So now all the scan points, as we lay in a pattern across the sample, are coming in as HDF5 files. You'll see master.h5. And they're all being auto-processed, right? So this is all happening live streaming, they're being auto-processed, and then we're running orchestrated workflows to actually extract the data. We'll render them in the portal so people can see what's going on. So you'll see an image of the 2D detector and you'll see an image of the plot. But actually, the most important thing is that this has actually calibrated everything automatically, has then taken all of the data sets and linked them back to all the other data about that specific sample in an automated way. And then it has actually then done what's called cake integration in two-dimensional X-ray diffraction that then has created CSV tabular data from all of that stuff. And the sample's done, and the sample heads out the door, and the robot will take it, and we get off and we make the next, we bring in the next sample. So I think for us, this of course is transformative because of the speed. It used to take an hour or two to do a single data point. We now do thousands a day. We do these in terms of tens of seconds, but we also get all the metadata right down to version control of all the workflows that happen on the data. The last one I'll show you really quickly is a laser shock station. You're looking at frames that are coming at over 1 million images per second in the high-speed radiography images here. And so you're going to see a flyer take off the little thing out in front, and that's going to smash into something. And then the data will be live streamed off an interferometer on the back surface of that, all the metadata extracted and curated. But also, as a stream processor, we're going to actually process that interferometry data and have all that data run as well. A really skilled graduate student used to do something like 6 experiments per day. This is miniaturized from a plate impact, which might be 2 experiments per day. And now we can do 1,000 shots in just over 8 hours. Right? So the thing has been transformative. And what I'll use the last part of my time to just sort of focus in on are maybe discussion provocations rather than conclusions, if you will, which is I think that labs of the future, if we're really going to make this work and scale, have to express knowledge in a computationally effective way. It was something that Joey said in the last panel about being computationally sympathetic. And that means full provenance. All the metadata and all the linked data are keys. It's not just getting the sample there and having those data then go somewhere. It's taking that data and linking it to everything that happened in your lab and everything that happened in some other PCL lab somewhere else where the sample might have been made, or when this sample then goes to a synchrotron. How do we keep that entire thread of data? I'll also say that automation of machines is software and software engineering, and it's really important. It's a problem that a lot of people work on, but automation of data is fundamentally semantic. We need to have that underlying formula and way that we think about samples and linked data to then express it in a knowledge format. And we can talk about how we do that in the lab if people want to hear more about it. The other thing I'll lean into a little bit is that a lot of this work is happening in isolation still, and we really need open foundations. I think those are an accelerator for this type of work. Things like developing the APIs, conformance testing, the semantics, the workflow interfaces so that other workflows can work together between different labs to really grow an ecosystem of labs. Authorization, governance, things about security and safety in labs. If we think about it, the web worked because the interfaces were open. And so we need to find that pre-competitive level, I think, for labs of the future to really accelerate and take advantage of that. So I'll stop there and let somebody else have the floor. Thank you.
Thank you very much for the introduction, David. I'll invite our next panelist, Peter, to begin sharing his slides. While you're doing that, attendees, please note that you can go to the Google link that was posted in the chat. There's a Google Doc there to post any of your questions. We'll have 2 sessions today, or 2 parts of the session to ask tailored questions, and then we will move to the audience Q&A at the end. Peter is the Director of Materials Platform Science at Lila Sciences. His company is building scientific superintelligence to solve humanity's greatest challenges. His team is really focused on the next generation of AI science factories. to tackle problems in material science. Peter began his career at NIST, building the Autonomous Formulation Lab, a self-driving lab program that applies neutron and X-ray scattering to autonomous experimentation challenges. Peter, the floor is yours for an introduction.
Thank you so much for the wonderful introduction and the invitation to share some perspectives. I have a very high level intro to sort of who Lila is and what we're the role that we hope to take in the autonomous community and sort of what our vision is. We're a Series A startup. They came out of the flagship pioneering incubator in Boston area, and we're sort of just now, we're in the Series A stage of sort of figuring out a lot of things all at once. So it's a very exciting place to be, and transitioning over from NIST has been a very fun experience. Lila, sort of top down, our mission, as Kyle alluded to, is it's intentionally sort of bold and provocative, scientific superintelligence to solve humankind's greatest challenges. And that really basically is rooted in the idea that the current existing corpus of data that exists, sort of that language models, for example, are trained on, is not sufficient to sort of achieve the level of machine intelligence needed to tackle the numerous challenges that face us across materials, chemical, and life sciences. And so we look really at building AI tooling that can tackle the entire sort of wheel of science, from model generation and hypothesis generation through to what is the right protocol to execute it, how do we really execute it, how do we analyze that data, warehouse it, interpret it, and ultimately pose the next question. And so what this looks like at a level that's not sort of just vibes is that we're building a new foundation model, right? A scientific reasoning LLM. And that LLM has unique access to sort of not only the conventional tools that you sort of might expect, like a RAG style base of human knowledge, but also things, advanced computational tools and simulation tools. And the most exciting part for me is that that intelligence also has access to what we call AI science factories. And so we've really taken a ground up approach at Lila in sort of trying to rethink labs of the future. And this is something that really lives in the name, right? What if we build something where science is not really a lab, but it's a factory? It's intended to run at scale, full performance, 24/7 operation, just churning against problems. And so this is kind of the vibe that we think about here. We think about sort of building labs of the future that are scalable, that are modular, and that grow out to address virtually any challenge. Where we've basically looked at applying this is not only in the life sciences, which is kind of where we came from, but expanding it to look at things like catalysts, coatings, porous materials, surfaces, chemistry. So everything, we've really taken all of science approach. And one of the founding theses of Lila is that when you're training a model, you can be better at all of science by doing all of science at once, right? It's something that I think a lot of people internalize at some level, that it's the cross-functional insights, right, between polymer physics and solid state chemistry, right, that actually lead to truly novel areas. And that's something we're very intentionally trying to exploit. And so the combination of that cross-domain learning with sort of vast amounts of data is basically our strategic angle on the problem. We have a really great team built out to address this, ranging from people that have done leadership under really complex environments, former Navy SEALs, through to people that shape culture, and a lot of really fantastic scientific minds that's a privilege to work with. And so that's sort of the 30,000-foot view of our sort of angle of the self-driving lab ecosystem. And yeah, with that, I think I'll try to leave some time for the panel. And then hand it back over to you.
Awesome. Thank you so much. And we have plenty of time for the panel, and I'm sure you'll get a lot of great questions. So next up is Jade's Zhu, and I apologize if I pronounced that incorrectly. But Jizu is an assistant professor of molecular engineering at the University of Chicago Pritzker School of Molecular Engineering and a scientist at the Center for Nanoscale Materials at Argonne National Laboratory. Her research integrates polymer science with AI-guided autonomous experimentation to accelerate the discovery of advanced functional polymers. She leads the development of Polybot, a self-driving laboratory that connects synthesis, processing, and characterization with AI ML guided decision making, and currently operates as a user tool within a DOE user facility. Her work spans electronic polymers, soft materials for devices, and sustainable polymer technologies, with a unifying emphasis on embedding circular design principles into next generation materials. And with that, I'll let you take it away.
Okay, thank you. Thank you very much for the invitation. And also, I'm very happy and excited to introduce Polybot to everyone. Yeah, I will share what I think the future lab looks like. And also, I would like to share the journey that how we build Polybot and also what we envision what will be the next state for Polybot. So the big idea at the beginning is pretty simple. So we want the lab to function not only as a place that researchers or scientists or students we just perform experiments. We also want the lab serve as a system that can learn, combining automation data and AI to help the student, to help the staff scientists to accelerate their discovery. So just imagine in a situation where given a task, given a question, then the lab computer decides what experiment to do based on its pre-learned knowledge and also the database. And then the robot carries out those experiments, upload the data, then the machine learning, and also AI decide what experiment to do next until it finds the solution. This is a very general concept. The concept will give the lab ability to serve not just a place to perform experiment, but also as our assistant to help us to accelerate discovery. So following this big idea, so since 2019, we have been developing a platform. We name it Polybot. My background is polymer scientist. I have a team with people background with automation, machine learning, IT, data, chemistry, and material science. I mean, they come together with Polybot name because we like poly means multiple potentials, unlimited potentials. So basically, Polybot has two core components. One is the lab innovation with pretty high level of complexity, and the other one is the decision intelligence. So on the side of the lab innovation, so the key point here is we need to embrace, not hide from complexity, because material R&D is complicated. We have to embrace it. So it is to integrate the workflow end to end, all the way from synthesis, processing, and also different type, different angle, different modality of characterization. So in a way that this entire workflow can help us to produce tons of data, reproducible data, and also high quality data. So then, as you can see, so there are many functionality we have developed in the past 7 years, I would say. We are following those 4 key criteria here. So first of all, we have to ensure the level of the complexity is sufficient. We're not going to sacrifice our science or hypothesis. We want the lab to be able to help us to reach that level of complexity to do that type of research. And the other thing is we have to be very creative in terms of to do many type of miniaturization of the instrument because materials are precious. We don't want to waste material, especially thinking about we're producing tons of data to train our machine learning model. It has to be small scale set. And the other one is I would say combine those two. Those labs need to be reconfigurable and also provide ability to expand a long time. So those are all the capabilities and the major capabilities we are currently have in Polybot. But you'll see like every 3 months we'll have more things coming in it. So then on the other side, the second part is the decision intelligence. Well, it is how we choose the experiment and how we extract knowledge from what we measure. So our decision intelligence has been evolving in, I would say, 3 stages. The first stage is really simple, is the efficiency. We use tools like Bayesian optimization to find better decision or better condition faster. The second stage actually goes beyond optimization into a learning period. We use machine learning to connect structure processing properties together, and we mine the knowledge from literature, pre-existing data, and then still use the self-driving lab to optimize the performance. Then the last stage, the third stage, is where we are currently, and we are heading in the future as well, is the adaptive human-machine collaborative decision intelligence. So in this stage, the system doesn't just propose the next experiment to maximize the metric. It also helps the students and scientists to explore hypotheses, navigate the trade-off, and make decisions wiser. So this is our current decision strategy based on very complex design tasks. So then we have already applied this approach in several case studies. For example, we have used this platform to develop high conductivity, low defect polymer thin films. We also perform the inverse design of electrochromic polymers, which can be used for smart window and make displays. And also we can also use this platform to help human to uncover the packing structure to transport design principles in the mixed conducting materials. So in each cases, the key value is not just only the speed, it's also the knowledge accumulation over time, teach us how to do research using data, using robot, and using those kind of fancy AI tools here. So yeah, finally, like stepping back, I think the labs of the future won't be a single lab. So this is showing the examples globally, not a comprehension list. So there will be an ecosystem. So for example, there will be like instrument platform that link to a central AI infrastructure, high performing computing, and also shared data standards. So our group role is to contribute both a working test bed and also a framework as a user tool in user facility to build this system. So what I will say that Polybot, the self-driving lab, will not just run experiments faster, it also sync with us. And also we would like to do this fantastic job together with everyone here. And again, Polybot is a tool for everyone through the user application. If you want to have a discussion, please feel free to reach out. Thank you.
Thank you very much for the introduction. I'd like to invite our final panelist, Taro, to share his slides. Taro received his PhD from the University of Tokyo in 1999 and began his career at Sony Corporation. He returned to academia in 2003 as an assistant professor at the University of Tokyo and was appointed a full professor in 2022. As an expert in solid-state chemistry, Taro focuses on materials for electronics and energy applications, particularly in the synthesis and characterization of thin film materials and surfaces and interfaces. Taro has authored more than an impressive 220 peer-reviewed publications and contributes his expertise to the Cabinet's Office Material Strategy and the Science Council of Japan. Taro, the floor is yours for the final introduction. We can't hear you. I think you may be on mute.
Okay, good morning. It's
Good morning.
6 o'clock in Tokyo. So it's my pleasure to show our direction of our research. So I'm going to talk about a little bit about modular autonomous experimental systems, what we are working on. So we demonstrated autonomous experiments in 2020, and then now our system has really advanced since then. And then our system is like this. So once we fabricate a sample, we want to do multimodal measurements, many types of measurements in sequence, and then collect a whole bunch of data. So that's our direction. So in order to do that, we have to collaborate with many vendors. I think the key for this self-driving labs is to collaborate with vendors. So like JO, Rigaku Shimazu, they are the instrument company. And then without their help, we cannot make self-driving labs. So what we want to do is to connect many types of instruments. But to do that, we have to think about the standardization. And then that is the barrier. So what I done is to talk with these vendors about the vision of the science and then what is the future of labs. And then they gradually understand and then they start collaborating with us. So we have to standardize like a sample size or this protocols when we connect the system. So it's modular, so it's like a plug and play. So we have to standardize many things to integrate all these systems. So the system is now looks like this. We have a sputter thin film deposition system, and the sample is transferred in the vacuum and directly into SEM EDS. So the sample is transferred through the vacuum directly. And the sample is taken out to air and many types of measurements, UV vis, Raman, and then electrical resistance measurement, and also like a X-ray diffraction. So we collaborate with Rigaku. This is one example of X-ray diffraction. So we have 1 centimeter, 1 centimeter size. This is size is all standardized for all the equipments. For this Rigaku one, so there's a shutter, automated shutter, and then Rigaku system would open the shutter, and then the sample is transferred, and the sample is measured, and the sample is analyzed automatically, and then it's used for Bayesian optimization. And then one important thing is that the data format is also unified, also standardized. So one problem is that there's many apparatus and the format is different. So collecting data into data lake is always a problem. So we ask all these companies to follow this MAMO or MIMO. It's an XML format. This became a Japanese industrial standard 2024. And these formats are outputted from every system. And also this process data is also outputted in a MIMO format. So all the format is unified and then stored in the data lake. So that is very important for collecting data. And finally, I want to show one paper. So self-driving labs in Japan. So this was published in Digital Discovery. And then in Japan, we have multiple self-driving labs and then spreading out the country. So I hope these labs would join to with or collaborate with other autonomous lab in the world for the AI for the science. Okay, that's all from me.
Thank you very much, Taro. Katelyn and I have divided up the panel discussion. She's going to start on the first topic in terms of data, and I will take over at approximately 4:18, 4:20 for a discussion on private versus public data sets. We'll open it up to the audience at about 4:30 for Q&A before we wrap up at 4:45. Katelyn?
Sounds good. Thank you again, everyone, for your introductions. They were very, really interesting and really useful. So kind of one question for the whole panel. Also, I think we need David pinned up here as well. I don't know who's pinning, but if you add him, that'd be great. Thank you. So for each of you kind of represent a different sector. We're looking at national labs, industry, academia, like domestic and international. I guess, like, what do you think each of your roles are kind of as we're going towards these self-driving laboratories, and, the management of data, in these labs?
You want to pick on someone, Katelyn, or should we just?
Well, you're chatting, so
Yeah, yeah,
you're
yeah.
gonna
You're
go
gonna
first
pick.
now.
You're gonna pick on me. There you go. All right. Yeah, I think in academia we have a number of different roles to play. Obviously, creating some new concept and ideas. I think that we are always mission driven by our projects, but we have uh, a little more freedom, perhaps, to explore new ideas and to make various types of connections. And I think on the data side of things is a place where we've really particularly leaned into that. I really liked what she was saying about making sure we have the level of complexity that we need and that there will be an ecosystem. There's no doubt. You want complex labs, but no lab can do everything, right? And sometimes it's for cost, and sometimes it's because you can't put a casting operation in next to a TEM and expect your TEM to ever work again, right? For an extreme version of that. Um, but I think that figuring out aspects of semantics that are sort of outside the realm of what instrument manufacturers would do and what a variety of people have to deliver product more quickly might do is a really important role for us. I think figuring out how one actually makes those connections between things. So in our group, we've worked very hard to create automated linked data through a series of DOIs and related identifiers. So metadata essentially creates the knowledge graph for us, and that's available, easily already scalable, and present. So that's nice. We'll actually have a manuscript going on that out on that shortly, which people can benefit from. And I think we occupy the role of creating as much open foundational stuff as possible as well. So I think those are among the natural things that we can do. And we also tend to span missions, right? If we have funding from different agencies see things differently. There are issues of authorization to use a lab, um, privacy associated with dual use data, and various other types of things that are really important. That if you have your own commercial lab and everything is internal, you don't have to face those types of things. And so I think that we get to do that and developing these new ideas of how one autonomously even understands data packages are things we work on.
Does anyone have anything else to add to that?
I can maybe speak to the industrial angle a little bit. I think it's really a complementary role that industry has to play in this in terms of the two things that come to front of mind for me are the first is productization, right? The incentive. I spent a long time in academia and in government trying to make the incentive structure line up for the things we were building to be really products that were taken up, and that there's ways that lines up, right? And there's beautiful things in open source ecosystems, but ultimately a company has an incentive structure that makes the long-term sustainment of platforms and things like that very easy, and sort of not reliant on public funding in an era when that reliance can be, let's say, treacherous. And so I think in terms of sort of building products that are useful to the widest swaths of industry is something that other companies are going to be very good at, and sort of sustaining platforms is something as well that I would say is a niche the industry is uniquely poised to fill. We're never just by virtue of economics, it's going to be really hard for us to be doing the best discovery science. That's just the deck is stacked against that, and so I think as much as possible, doing this sort of cohesive work is our goal. And especially you see that as Lila looks to integrate with language models in a way that would be just from a token cost alone would be really prohibitive to do in other contexts. So I think that's our niche, and I think it's an ecosystem where every category certainly has a niche to contribute. Right, industry alone could not build this. That feels important to say.
Yeah, I can speak from kind of national lab user facility perspective. So usually in user facility, we kind of provide shared hardware infrastructure, and then staff scientists with their domain expertise in methodology, in instrument, right? And also we work together with diverse users who bring their own domain expertise. So therefore, a long time we actually can establish a library of protocols, standardization methodology for different type of applications. So those are kind of the exciting side, the good side. Then documentation, where documentation on all this is really challenging. So, but we have to do that. We must do that, especially now we see we are at the AI age. Then we see the needs of high quality data. So then as a user facility staff scientist, we have our certain time committed to documentation and then to do those type of work that may have low visibility, but will eventually have a big impact. I think this is probably the unique contribution that can coming from the user facility.
So I can add a comment on our role from academic side is that how to spread this technology to many people, many companies. And from my honest view is that the autonomous or automatic experiments is not so spreading fast. Once early adapters used it, and then less followers. So that's one problem I feel. And then we have to do many standardization or make many things simple or educate the person who can run these or set up these systems. So that's our challenge now. So how we teach and educate is really big problem. And then for the chemistry, material science students, they have to learn about AI, they have to learn about robots, and then so many things to learn. So collaboration between AI researchers, robotics, and material scientists, those are becoming more and more important. So we want to set up those environment. So that's what we are doing right now.
That makes a lot of sense. Thank you all for your answers and your insights. So I guess another question that kind of like a overall question as well is it's a couple questions and take it how you will. What is the kind of quote unquote data compact for shared use? Like who owns this raw data and derived features? What are kind of like the workflows? Who owns the workflows and the models that are created, as well as what are the incentives that make anyone willing to contribute to high value data sets or, help create them? Um, I will pick on, I guess we can kind of go if one or two people want to answer that, but I can pick on, I guess, Jay.
Yeah, I can speak from user facility, like because we have users, they are producing raw data on every single instruments, right? I would say in user facility, most of the time, the raw data are stored in the equipment computer, for sure. And also the workflows as well stay in the computer. Now, most of our users are actually coming for research purpose. So users own their data, but since their purpose coming here is for research and majority of them are published, then so once they publish their research work, or if we can gain the agreement from them even before they can publish their work, then we can use their raw data and we can use their model as well. The workflow stays here. So the workflow, unless there's a pre-agreement ahead, otherwise the workflow is kind of the knowledge we learn from the users a long time that Polybot and also user facility capability get involved as well. So then for the database that user facility can provide for other people to access. So this is actually a big task for us now. So we are currently at Argonne CNM Nano Center, we are developing data management platform that can help us to well organize those kind of massive data, but we want to reuse the data. So then this need a lot of effort to label the data well so that people can gain high quality data. So I would not say this data management platform is ready, but this is the current effort putting in to make sure we have high quality data that can be reused again and well labeled. Yeah.
Does anyone have anything else to add? Question. Yeah.
Yeah, I'll jump in and say that, across projects, we dovetail data management agreements with the project funders. Of course, every funded project that comes through the lab has some sort of data management, and there are public access plans from those funders that have to be adhered to. And so sometimes that's very forward-looking. In the paradigm MIP, all user data becomes public after 1 year or upon publication. Unless it's negotiated to have another agreement ahead of time. There's always, reasons for data to be private because it's sensitive. There's IP, a variety of other different things, obviously. In our lab, we actually honor the project that comes to the lab's data agreement. We are starting work with some outside companies now and have NDAs with them. And that data, of course, will be handled quite differently than data that goes to, well, it is in Paradigm as well, but goes to academic projects and the like. In general, though, we still conceptualize the idea that the data belongs to the people running that project, although there's not really legal governance that supports that. I will say that the community, the Pharos community, feels very strongly these days that those who produce the data are being shortchanged by those who use the data for AI. So one thing we also lean into is that full provenance on the data and adherence to FAIR principles allows us to exert governance, whether we necessarily know what that governance should be at this moment in time or not. At least we have visibility through the metadata to do that.
Yeah, I would maybe add as a concluding note, I think it's, I as a former user facility scientist, it resonates to me that public data is kind of a public good, right? I don't think, if work was ultimately publicly funded, subject to some, of course, time and manner restrictions, I think exerting control over derived products is a little bit, attribution is one thing, but I think ownership is difficult. But a lot of the most compelling sort of corpus of data is, lands in the firmly proprietary space, and there I would say that the era where you could distinguish between the data and the derived models is long gone. That cat is out of the bag, and everyone would like their data siloed. So that's I think it's a strong argument for open scientific data as a public good that enables advances, right? The fact that vendor A's data will never contribute to a foundational model because they don't want that because it might help vendor B means that you need open data fundamentally. So.
Awesome. Thank you, everyone. So I'll have one more question, and then after this, we will switch over to the kind of the policy discussion, which you guys are kind of getting into now. So I'll ask this of Taro first. So with your model or with your self-driving lab, you have included machine learning into the process. So it's how did you train the model initially, and then how do you update the model, especially as you have new samples that are added to that you measure and synthesize. So how do you manage all that?
So you mean this, so we use Bayesian optimization. So you mean that how we train the model? So
yeah, okay.
Yeah. So what we do is that when we do Bayesian optimization, if we just bring in the hyperparameters used in like information science or internet business, then it doesn't work. So we have to tune the hyperparameters or Bayesian optimization suitable for material science. So that's very important to reduce the number of experiments, the number of trials. So we use domain knowledge to tune the hyperparameters. So we know the process window, how we, as a scientist or chemist, we know how many local minima in this search space. And using that data, we simulate first and then set the hyperparameters and then use it for the material science experiments. So domain knowledge is very important to run or train the machine learning. That's our experience.
Awesome, thank you. And so with that, I will transfer it over to Kyle for the second part.
Thank you very much, Katelyn. So, we've got two researchers here from university, one national lab, of course, user facility, and one from industry. And across the board, it's great to hear that everyone thinks data should be open. That's fantastic. That cuts out like half of our questions. So instead, let me flip another one around a little bit. Traditionally, across the board, any publicly funded work has an open data mandate. And like you mentioned, David, that's 1 year or whenever it's first published. Makes sense. Is that the right model? Is that the right policy to go with the advances of autonomous laboratories? Or is there aspects of that that should be revisited? And David, I'd like to hear from you and then also hear from Peter at the end of that.
Yeah, it's a good question. I think that I'll sort of jump a little sideways on it, right? I think Peter mentioned the cat's out of the bag. I think the really complex place is not so much what happens with data that's going to lead towards a traditional publication or even the dark data, which one of the things none of us bothered to mention, but we all know is that in these automated labs, we get all the data, right? The failed and the good and the bad and everything. So that's a huge advantage. And if we semantically control it, although there are some gaps in how you even semantically describe things that don't work, but that's very powerful. But I think that the place that we really have almost no insight is in once you have a trained model, right? If you're not just putting that into analyzing the data, doing some visualizations, extracting something, if you have a trained model that uses that data, how does one even know what the data are in that, right? We have arguments about from a national security aspect when you're given an open source model and there's the code, but you don't know that the weights are really trained on what you think they're trained on. You can't tell. So I think something akin to sort of an NFT type of approach for being able to track provenance of what has happened in models would be it's a high level research problem in computer science, but I think is something that would really be the next step that then could drive policy if we could really tell where things are. That's my take on that. Otherwise, I think that the specifics of the public access plans, those things grind pretty slowly in my observation at the national level, and I think they've come a long way in the last decade. So I think they're pretty great. I'm sure if Jim Warren's still on the call, he could weigh in on that, or any of the folks from the first panel yesterday with a lot more knowledge about what's practical. But the missions of the different agents. Yeah, look, I brought him in. So
yeah, Jim, it'd be great to hear from you.
Yeah. Hello, everybody. I'm sorry, Dave. I missed the actual question you were asking.
The open data mandates and the public access plans and whether that needs to be revisited. Is it does,
So maybe is that a conversation for now or is that a conversation for later?
Probably later, I think, but it's an
active
learning conversation, I believe.
All right. Well, then I'll leave you all back to your panel discussion and we can have that conversation at a later time.
So Peter, as an industry member and probably a strong user of the data set, much less a creator, what are the differences there?
Yeah, I mean, actually, a lot more alignment than you would think, right? I think dark data is sort of holds the key to capturing real scientific insights, right? Papers are one very filtered view of science, and from our perspective, if you want to teach a model to do real science, papers are actually a very poor way to do that because it's sort of a success-only story of something that everyone here knows is probably, if you're batting 50%, that's really good. And so I think, in terms of drawing it back to that original question of, is a 1 year embargo period, what is the policy answer here? I think it's a little bit, I agree that strides have been made, right? In terms of even having open data policies at all has been sort of a large shift. Um, I don't think the policies have yet really reckoned with what a derived product of open data is. And I'm less worried about sort of extracting economic value from that data. Given that the data is public, that's sort of its own thing. But a lot of sort of career and reputational value hinges on data generation. And currently, citations on a paper to scientific data aren't it if you're making a tenure case. And so I think the real questions here are about how we handle attribution and proper credit for databases, especially where that data is sort of siphoned en masse into things like model training, right? I think we're just beginning to see the societal implications of this, and and you look at the large frontier AI labs and where they've grabbed their English language training data from, right? I think you're beginning to see sort of a lot of grappling with the societal question that's maybe not even well posed yet. And so I think I'm not sure I have a concrete policy thing proposal there, but I think it's an area where we need to do some real thinking.
Fantastic. So Ji, I want to pivot to your user facility. As everyone knows, a national lab user facility is, well, meant for people to use. You've done a lot of work and a lot of effort so that people can come leverage this equipment. What's your opinion on interoperability across the sector? What should be in place such that people could potentially leverage multiple autonomous laboratories cohesively?
Yeah, so just inside of Argonne, we have several self-driving labs, right? So then for each self-driving lab, they have their own like infrastructure, or I would say complementary capabilities. So then the way that I see currently with another user facility, Synchrotron APS. So we have also self-driving lab in Nano Center and also self-driving lab in the X-ray sector. So then because we hold very complementary expertise, one is more towards material synthesis and property evaluation. The other one is more towards morphological multi-scale like structure characterization. So this is a very good marriage to combine two complementary self-driving lab to pump in and fill in knowledge from different purpose. And they are, well, I think the lower barriers we are kind of managed in one system, then it's kind of lower the barrier for us to share data and also communicate through one network, right? So this is kind of a seamless integration with two self-driving lab with complementary capabilities and providing complementary knowledge for pushing one type of material discovery. So then in terms of other self-driving lab sharing outside of national lab, ours outside of user facility in DOE. Currently, we are kind of leveraging discussions and meetings to see how we can use what they already developed. For example, data management platform, what are the components we can use and learn and use in our system? So that's kind of something we are currently doing, but not yet seamlessly integrated like what we are currently doing with APS. That's kind of the status. Yeah.
Very interesting. Any other comments on that from the panel?
Yeah, can I jump in on that, Kyle? I think that I really like what she has to say. I think that there are other pieces to it as well that I would emphasize, right? That there are that the national labs and the government labs, funded by other agencies other than DOE, have fantastic facilities and have people dedicated to doing these things. And I think that academic labs often represent just an extraordinary continuum of capabilities and ability to respond to those things. So sometimes they leverage things developed at national labs, and that's great. And other times, the national lab perspective is very different than what an individual investigator who has a lab at a university might have, or one of us who's been working on one of these super duper kind of labs at a university. And so I think finding the commonalities of how we connect all those things is really important. And I think eventually it has to be truly innovative and not one-to-one negotiated. I was at a hackathon Paul Scher Institute in the fall in Europe, and Europe has a very coordinated view of these materials platforms. And but it's all one-to-one. It's like I will tell you what is coming in my data product that you then will be able to write code to understand. And ultimately, we need those data products to be transferable in ways that I can send you something and I don't tell you what's in it. And that you can then take that apart and use it, right? And we can use AI to do that work with sort of a minimum viable ontological description. We in our group are packaging things in RO Crate and doing a variety of things, not to get down in the weeds, but I think that having those types of conversations will let all these pieces start to play. That's my take.
Excellent. So I've got one more question, David, particularly for you and Taro. We in the realm of autonomous laboratories, the amount of data that produce is just dwarfs everything else in publications, right? With that, I would say maybe becomes a different set of liability for people that use it just by quantity alone. What do you, between you two, David, Taro, what do you think changes in terms of a researcher, an institution, or even a company's liability in producing data sets at this scale?
I'll let Taro go first, and then I can tell you what we do. You're muted, Taro.
We still cannot hear you, Taro.
Sorry. So
There
your
you are.
question
Thank
is
you.
that your question is that you mean the role of our researcher in making data?
More specifically, with the quantity of data that's being produced, that
Yeah.
increases the adoption, the widespread use of it. Do liability rules change for an institution, for an organization, or even for an industry partner?
I see. So it's true that the whole bunch of data is formed, and then let me say a word after David.
Yeah, I'm happy to go first then. I think there are sort of two pieces to that immediately that I would jump in on. One is, of course, the amount of data is large, and I think that's complicated for all of us, right? There's an expression, data has gravity. So our data center here, we are scoped at 100 petabytes, and we host several data sets that are in the petabyte scale. And then we routinely in our lab can crank out tens of terabytes in a very short period of time, right? So that adds up. National labs face these issues as well. And so having a true data center is important for doing that stuff and being able to handle that. But ultimately, then you need to also co-locate compute or have very smart systems to be able to extract exactly what data, query out the data, specific data you need that you're going to move and do compute elsewhere. So the idea of locating compute close to the data is something that has grown actually out of the Alex Saleh and the astronomy group here and Jim Gray at Microsoft. So we're pretty comfortable with that and with how we handle our data and building the right kind of infrastructure. When it gets bigger, though, there's a liability, I think, on two sides that I see immediately. One is responsibility to actually be able to continue, sustain, and curate that data over time, including backing it up and all manner of things like that. The expense grows quite rapidly. But I think the liability that you may be alluding to is what's in that data and what use people make of that data, and the fact that we can't really have eyes on that data anymore. I'm not sure that that's what you wanted to get at, but certainly that is an interesting problem. There's liability on the side of how the data is kept private and kept out of the wrong hands, but also how the data may be contaminated and put into hands on purpose to do a variety of other things. National Academy report a few years ago reviewing DIMREF, I think, was the particular report that mentions some of that. We mostly right now are focused on how we make sure that data packages that come to the lab to actually operate the lab don't bring problems to the lab, right? First step is nobody wants to break their lab. So that's a thing. But we've got a high energy X-ray source and we're firing a high powered laser and we're doing a variety of other things. So there are also safety issues associated with that. And then in synthesis, there are issues associated with what's safe to do. So we're mostly focused on that, but I think it's an excellent point and one that, in my experience in the data world, we're only starting to scratch the surface on. And it scales very quickly when the data gets so big that you can't really deeply know what's in it all.
Fantastic.
Yeah,
Tara,
so
any brief comments
yeah.
before we move to audience Q&A?
So what I face is that so much large data is generated, but ourself cannot analyze all. That's why we want to share, and then other people analyze those data. So this sharing the data, and then other people can manipulate those data. Those platforms are still not constructed yet. And then the software that analyze those data, those are more user-friendly data analysis software. Those are needed to really use fully the data. So that's what we face right now.
Excellent. Well, hey, thank you all for a very great discussion. I'll turn it back over to Katelyn to cover some of the audience Q&A that we've got in the Google Doc.
Awesome. Thank you. So we have a couple questions from the audience, and the first question is from Rushik Desai, and I can read it, and if you want to clarify anything in it afterwards, please feel free to unmute yourself. So they asked, when do the AI models become ready for production-grade experiments in the labs of the future? What are some metrics that you look at before making this decision? Then they have a follow-up. Hey, yeah, Peter, yeah, you did go for it.
I mean, to me, it's I think if you're, I guess ready is a word that has a lot of axes, so I'm going to pick one meaning. To me, I mean, I think your lab's safety guardrails in terms of, in the biosciences, you have to make sure you're not making a pathogen, right? In the material sciences, we have to make sure we're not shooting X-rays across the room or, or making something that's pyrophoric, for example. But, those guardrails, I think, should live outside AI land for now. There's versions where that does move into AI land. But within the realm of safety things that are outside of your decision algorithm, I think this is a thing that proves itself by doing, right? Your AI algorithm is ready to guide the experiment when it starts making choices that are better than a human. And the only way you can do that is by letting it go. And the first time I ever let Bayesian optimization drive a self-driving lab, it immediately made 5 of the dumbest samples you would ever think. And that's how this thing works, and you get better. And so I think it's important that the guardrails be separate, and once you do that, you can really test your optimizers. In silico validation is another thing that's hugely important, but maybe I'll give other panelists a little time to comment.
So if another panelist doesn't have a comment, I could also read the follow-up question they had to this.
I mean, I think Peter's picked a good direction. I think basically, of course, the answer depends on what you're asking that AI model to do, right? If you're asking that AI model to simply decide to go to different places to run more characterizations that are going to be useful, and there's not a lot of risk in that. And so it's ready as soon as it's making predictions. If you're asking an AI model to think of some really new chemistry to do, then you need to have some way to know that you're not going to make cyanide gas when you mix those things together, right? Or something else. So there's a whole spectrum there. I think the metrics are quite complex because the AI model metrics themselves are not really germane, right? They talk about how well it matches some data set in a variety of different ways that may or may not be intuitive to science investigators, but I don't think that they really play. I think the underlying paradigm shift that we think about here, and we have some ideas on, and I'm sure others do as well, is how we think about compliance and governance going from sort of procedural compliance, like don't have the robot move the sample over here, it's going to wreck the detector, right? Make sure the door is closed before you turn on the x-rays. Like we can make that list and that list gets better. But then when do we actually get some sort of like machine enforced risk governance when we can trust an AI model to take new information, right? We know that we can get emergent types of out of distribution thoughts from sort of these agentic clusters and things like that. And I will tell you that I don't think any of us will want to trust those with something that's really dangerous for a really long time yet, until we feel that we understand those much better. I think all of us are thinking, well, many of us are thinking about how we design that to happen so that we can actually allow AI to do it. But those of us who have had switches in systems so the AI does our, you know, spam email filtering know that it's not a very good system yet. So.
And Taro, did you have anything to add? I saw you nodding along. Just wanted to double check that you didn't have anything. Okay, sweet. So the follow-up to that was also from the experiments performed by AI, do you think there could be cost savings in terms of the resources utilized since AI would make quote unquote more intelligent decisions? Or is that not something that factors into the use of AI in these labs? Um, yeah. And so if anyone wants to answer, is he, all of you are unmuted?
Cost saving.
Yeah.
Number of experiments increases, but so the number of experiments increase means the cost increase, but the sample size decrease. So the cost would decrease, but in total, I think the number of experiments increase means that the cost increases. That's my experience.
Yeah, I can share my experience. So I think another benefit I see the AI role in the autonomous lab or assisting students research is that AI provide a lot of data analysis to piece human mind in terms of the stress in making decisions. So for example, my student, when they are facing complicated design, then first of all, they are afraid of making decisions that cost a lot of time. That is also a cost, right? So then they are struggling here in terms of making decisions. Now, when they are seeing the statistics provided from the data analysis, then they are more comfortable to make a decision and moving on. And they are not afraid of decision making because this is an active learning process. They are keep seeing the updated result statistics. So the other thing is because it's performed by robotic system, we are kind of less likely to adopt the reproducibility. Because when students do the experiment, when we are doing the experiments by different people, then we are always concerned about the muscle memory caused the error bar here. So then from those kind of robotic experiments, usually once the result pass the t-test, we set ahead to ensure the reproducibility. We usually just trust, then we will not waste another kind of effort and also material to redo the experiment to just keep tracking and checking. So I think in this way, I'm just thinking from a different angle. So AI and data analysis and the statistics kind of save people's time to make decision that save effort, save cost, and also the robot enhance the reproducibility, and then the t-test, another statistical analysis, help people to ensure, okay, we don't need to do repeated experiments again and again. Yeah.
Awesome.
Yeah,
Thank you. And
I think there's, sorry, Katelyn, I was just saying, I think there's no doubt that for most things, we think of it as cost saving, right? We can do things faster. We can take an optimization path that gets us where we want to be if we know where we want to be faster. And if we're mapping out a huge parameter space, um, if we find nothing, then yeah, I guess that was not a cost saving. But mostly, I think most of us think we get there faster. It's a very MGI-ish feeling thing. We get there half the time for half the price. Well, It's not quite that kind of an equation necessarily, but I don't think the startups would be doing it if they didn't think that it was going to pay off as well. So,
Makes sense. And I do want to make sure to get to these last couple questions. And
yeah.
so, I guess one person can take this one is how can individual PIs with small labs collaborate with or compete with autonomous labs in the future of large laboratory ecosystems? How do individual academic PIs adapt? So, um, maybe like Taro or she, like I think might be.
Yeah, this is a very, very important question. So, yeah, one way is to share the autonomous labs so that the small lab PIs can use those facilities. So sharing is a one key. That's my opinion.
Um, I think National Lab has kind of its unique resource in infrastructure. For individual PI lab, I would say we will have some parent infrastructure similarity overlap across different labs. I would say use the user facility infrastructure as much as possible because they have the staff trained to operate it. And based on my observation, at least at current time frame, it's not reached to the maximum capacity. It's still, allow more user to access this infrastructure.
Yeah, I have really strong feelings about this, Katelyn. I was starting to type it, but I'll just spew it out. I don't think PIs should have to think that they're in competition with these labs, right? The future is complementary, right? It's being able to put these pieces together. And if these so-called labs of the future do their job right, then all the labs are labs of the future. The long tail is really important. And there should always be labs where people are doing innovative things and different things and looking at different things. And we need to be able to integrate that and also lift it up, not leave it behind. So uh,
Yeah, I would maybe to add a voice that in the same direction, right? I mean, we talk a lot about science factories, but I think it's important to say there's a subset of science that should be done in factories, and I think there's a place for frontier discovery science. And I think community infrastructure is the key to it. User facilities, and especially the more that user facilities build on modular and reusable components, it preserves a lane for that discovery, whether that be of new automated unit ops or of new optimizers, right? As much as we keep modular and open frameworks, there is a space for that frontier discovery to be done by basically anyone. And so I think there's still a very valuable role. I don't think it's competitive at all.
Yeah,
Awesome.
that's right.
And
I want to add finally.
yeah,
No, I
I'll
think
let
that
Tara be the last voice.
yeah.
Sorry, go ahead.
So the experiments that can be done using autonomous or automatic experiments is very limited compared with the large material space or how we do experiments. So human can use their creativity or their hands or feelings or sense to do many, many experiments. So that's the strength of human. So combining those human strength and with those autonomous research, that can be done by the small labs. So human can do a lot more flexibility. So that's a strength. That's all.
Awesome. Well, thank you, everyone. We are at 4:48, so I don't want to eat up any more of today's time. Thank you, panelists, for your introductions and your thoughtful comments and answers to questions. And I guess with that, I guess we're handing it back over to David for the closing.
yeah, too
Yeah.
much, David. Sorry about that, everybody. Should have had somebody else close, but thank you to the other panelists. That was really enjoyable, and yeah, to Katelyn and Kyle for making that happen. And so that does bring us to pretty much the close of the day. And so I think hopefully. People enjoyed the panels today. Maybe I'm not very objective, having just sat on the one panel, but I thought that was a really interesting discussion, and was really pleased that we were able to hear from different types of stakeholders. And I thought the industry panel this morning was really spectacular with lots of really great commentary. And I took a lot of notes and good things to talk about. I don't, because I was just doing that, I don't have the agenda to pop right up in front of you all, but I think everybody sees it and knows about it online. And tomorrow we have, oh, wait, there, that's quick. I've got it now. If I get to this window, all right, I can't get to that window, so never mind. You can look at it online. Tomorrow morning we have, or tomorrow afternoon Eastern time, sorry, we have another couple of great panels. One is on workforce development at AI speed. We've been doing a lot of work in MaRDA and in the Martian Materials Research Coordination Network funded by the NSF on something called Fair Train and helping students learn to share data as they make it in curriculum in actual laboratories while they're doing regular courses that people take in material science or mechanical engineering or civil engineering, and having that be regular. We now, of course, like everyone else, feel the need to understand how AI gets incorporated in that, not just taking a course and learning about AI, but really bridging to how AI will be educated within our disciplines as a normal use of things. So there's a great panel that'll be run tomorrow morning by Olga Wodo from the University of Buffalo, who leads those fair train efforts. We've got panelists Joshua Schreier from Fordham and Gilad Kuznev from NIST, Arun Manodi Kanakikudi, sorry, Arun, from Purdue, and Sterling Baird from Brigham Young. So that's going to be a really interesting panel, people who really think about education and doing it in very different places and workforce development, even beyond university work. And then we have a really interesting panel for the second part in session 6 tomorrow on AI-ready data and materials data repositories. That's going to be moderated by Jane Greenberg from Drexel and Matthew Evans from the University of Cambridge. And we have panelists from the Materials Data Facility and the Garden Project, from NanoHub, from OQMD, and from the European perspective, from Nomad and Fairmat, and how that data system is being sustained by spinning out use in different places. We also get to close the day with the outstanding poster awards and presentations. So we've now had our poster sessions, and there'll be a best poster award for student and a best poster award for postdoc, and they'll get a chance to give a short presentation. So I know the third day is harder for people to get back, but I hope people will come, and we'll stay to the end of the day to really celebrate the work that our students are doing and that this next generation are really working on. So with that, I want to thank Austin Tremblay again for making it all happen in the back end, and Selena, and all our panelists today, and moderators, and everyone else who came and asked questions, especially Taro for joining us from a very distant time zone. We really, really appreciate that.
My pleasure.
So thanks. And if
Thank
no
you.
one else needs to say anything, we are adjourned.